answer. Maybe we'll make an Excel, but not today, where we can play with the parameters directly. The question you have to think about, though, is that you're right, that B will B accumulate is the question. Because if B to C happens at low temperature, and you're already at a pretty high temperature, then you might not really see much of an accumulation, and so instead it's kind of like as soon as you make a little bit of B, it's just consumed away.
If you hit 100% conversion before the other curve, before the other one starts moving up at all, then yeah, you won't see it. You would see it more. But like if you're only hitting some sort of percentage,
right.
you'll still see it.
Yes, that's the point, is that you might hit 100% conversion before the sweet spot occurs, or you're past the sweet spot. Yes.
Can the reaction from B to C be like endothermic?
Sure.
From A to B is exo?
Yeah.
So then making B heats it up, which makes B to C happen less because it's or no.
Happen more.
Yeah. But then, like, if you switch from there.
Remember that rates always go up with temperature, right? But now what's going to happen as B to C starts to happen, it's going to cool the system back down, and so you kind of have a compensation effect that occurs within the generation term. You might not always be increasing in your generation term. You might decrease at a certain region and then increase back up. And of course, it can get even more complicated if you have a mixture of series and parallel reactions. Yeah. Parallel reactions are more simple to think about, right? Because it's just however much of each is happening, and they affect each other, but not as much as series reactions can affect each other. Yeah?
The way you wrote it down there, you just treat it as if it was just one single reaction, right? You can treat B as an intermediate, as if it wasn't really.
Right. If B is consumed so rapidly, it's almost like a transition state or something. It's almost like something that you never really see. It never really appreciates in the system. And so, yeah, it's effectively very similar to just if I would have written A to C. That's another good way of thinking about why you might only get a single hump, is if B never accumulates, that could be why.
And that would be PSSA, right? Like you just assume that B is.
Yeah, I mean that is one of the pieces of a PSSA assumption, but you don't need to worry about PSSA for a CSTR. It's already a steady state, right? Yeah.
So it looks like C is a stable, steady state at around the medium conversion range.
Yes.
This is unstable for the single. So would people design a multiple reaction in order to be able to operate there?
No, I don't really think so. No. I mean, multiple reactions exist or they don't.
Right.
You can't add a reaction to a system.
Well, I didn't.
You could add a species,
right,
but yeah.
That would introduce a second reaction.
Yeah, maybe you could think about doing that. I don't know. I'd have to think about it more. So that brings me to another question, and it's hard to tell on here, but where is the ignition point for this reaction? Maybe if I draw it a little bit differently, because this one is kind of boring the way I drew it. But what if this comes down like this?
It's still going to be 2.
Yeah, that's the kind of point. That's the point I was kind of after. That should be a straight line. I know it's not. Is that you can kind of have 2 ignition points. You can have this point, right? And then you're going to jump up to here or something. Again, straight line. That should be parallel to this one. That's not going to look nice. It can jump up to here, and then you can have another ignition point here where you can jump up now to this even higher point. So just something to keep in mind is that when you have these multiple reactions, you can have multiple ignition points. And that kind of maybe makes sense in your head because an ignition point is often defined for a single reaction, right? So if I have 2 reactions, I have 2 ignition points. Yeah.
Couldn't one ignition lead to another, like immediately? So it'd be like
I mean,
superignition?
if I drew this a little bit differently, if this didn't come over so far, then this might miss that second hump altogether and just go straight to the high temperature. And that's what you're describing is, yeah, you get to such a hot temperature that it kicks off the second reaction to essentially complete conversion as well.
Could you fiddle with like whatever's in the R term to get that slope to be a little bit lower?
Yeah, I mean, yeah, you can always control R by changing things like the initial temperature of your feed and the temperature of your cooling fluid and the heat capacity of your reagents by adding inerts or other things.
So
all of that changes the slope of R.
basically, like when people run something like this, would they try to make the slope of R be as large?
No, you'd want to get out of this region altogether. You probably don't want to operate where there's so many steady state solutions. But no, I mean you can manipulate the right to change that slope. And that's part of how you can avoid the multiple steady state solutions, right? But obviously it depends on what are you after. Do you need to avoid that high temperature for some reason? Then obviously you don't want to make the slope too low or you're going to hit the high temperature point. Okay, so now let's switch gears to a PFR. And instead of series, we're also going to switch gears to parallel. And instead of all the stoichiometric coefficients being 1, we're going to have numbers. So a few changes. So this is example 12.5 in the book. Except he's got a typo there, big surprise. I'm going to leave this off for a second, actually. All right, so we have A goes to B. In reaction 1, reaction 2 is 2A goes to C. We have a pure A feed, a PFR. It's a gas phase reaction. The inlet temperature is 150 Celsius or 423 Kelvin. The initial concentration of A is given 0.1 mole per liter. And it's asking us to find the temperature as a function of the volume of the PFR, or you can also think about that as the profile of the temperature along the length of the reactor, and the flow rate of each species in the system also as a function of the volume. Other information that's given is negative delta H for reaction 1, negative 20 kilojoules per mole of A. So I can put an A there, all that means. Negative 60 kilojoules per mole A. So again, we've got two exothermic reactions. The heat capacity of A is equal to the heat capacity of B, and that's 90 joules per mole Kelvin. So what's delta Cp for reaction 1? The heat capacity of C is 180. So what's the delta Cp for reaction 2? Also 0. 180 minus 2 times 90.
Should we practice ones without delta CP being 0?
I mean, I don't think it requires much practice, but I wouldn't forget that the energy balance exists without that term in it. You know, I wouldn't only put on your notes like the energy balance is without it. You get a whole page front and back, so you'll have plenty of space.
So we will have one on the test.
No, I didn't say that.
Do you mean to have the enthalpies be exothermic?
Yes, both. Oh yeah, sorry. Good catch. Those aren't the negative delta H's, those are just the delta H's. All right, UA is equal to 4,000 joules per liter second Kelvin. The temperature of the cooling fluid is 100 C, aka, and it's at such a high flow rate that it's constant. And K1A is given by 10 times the exponent EA1 over R 1 over 300 over 1 over T. And that's in units of inverse seconds. for this one, the units are liters per mole second. And that's because, these are elementary, so you're going to have a concentration of A squared. But I'm going to write down the rate equations in a minute. Okay, so that's all that we're given. Any questions about what we're given or what we might need?
What is EA and B?
Oh, yeah, I didn't give you that. EA1. It's actually given in the example as EA over R, so it's just saving you a little bit of math. EA divided by R is 4,000 Kelvin. EA2 divided by R is 9,000. Any other questions? Okay, let's start the problem. Where do we start it? Material balance. We're going to leave that up there. Okay, so the material balance on each species, right? That's what we do for multiple reactions. So the change in flow rate of A per volume is equal to what? Anybody know for PFR? It's the net reaction rate. Again, reminding you that it's a net rate. Okay, so what is the net rate of A? Negative R1A.
The net rate of A or negative?
The net. Yeah, that's why this is, right.
Minus 2R2. Wait, hold on.
Okay, so the minus we got, and I think everybody can agree that R2A is going to go here.